Hi, we are Anand Srinivasan and Naoya Takeshi, and we'll be talking about an MC-MC method for uncertainty set generation using operator theoretic metrics. So in real-world situations, we often encounter plant model mismatch. This can be due to process noise, observation noise, or simply finite data. And the set of models which we expect the plant to be contained within is often referred to as an uncertainty set. And generating this uncertainty set can itself be a challenging modeling problem, and this often arises in robust estimation, prediction, and control problems. So we'll start with the general framework of uncertain optimization and move to the dynamic setting. We have some real valued objective f given some argument space x, which might be control inputs, for example, and a parameter space u. And uncertain optimization can have two standard formulations, where on the left, we have the minimax or the game theoretic version, where we try to minimize the worst case cost with respect to all possible parameter settings. On the right, we have what's often referred to as a robust optimization problem, where we have a nominal parameter setting u naught, and we minimize costs with respect to some constraints imposed by other parameter settings. Now, choosing this parameter space u entirely determines the goodness of the minimizers of these two problems. This is referred to as an uncertainty set, and selection of u is the focus of our paper. So as I mentioned in dynamics problems, x is typically a state estimation, a forecast, or control input, and u will be our dynamics model of parameterization. And configuring the space of u for general dynamical systems is not well defined. So we'll start with a simple base case where we have a finite dimensional linear system represented by matrix A. And we'll consider sort of a base case uncertainty set as additive perturbations of A via this perturbation set delta. Typically, this delta is bounded by a norm, where the norm is given by the standard metric on Rm by n. And this delta may have some structure, such as diagonal or block diagonal. And this immediately raises two questions in the general dynamic setting. The first one is, how do we use such a formulation to handle nonlinear dynamics? And the second one is whether the standard metric on Rm by n is necessarily good for comparing two dynamical systems. And for the second question, we have some preliminary evidence from this graphic on the right that the answer is no. So here we have Gaussian perturbations of a LTI 2x2 system in the unit ball, viewed in the trace determinant plane. So here we have the nominal, which is a spiral source system. And even with fairly small perturbations, we venture into distinct dynamic regimes, like saddle or even spiral sink. This suggests that while two representations may be close in some default metric, they may be distant in some dynamic sense. And so to answer the first question of how to handle nonlinear dynamics, we'll move to the transfer operator description, which is often used in mathematical physics. And in a nutshell, the transfer operator description consists of lifting nonlinear state space flows f to linear function space flow operators k, where the lifting is performed by these observable functions phi. When these observable functions are arbitrary complex valued functions, k is referred to as the Koopman operator. When there are probability measures, it's referred to as the Perron-Frobenius operator, although these are used interchangeably. What's nice is that this operator k is fully linear, and it is related to f by this commutative relation. And this allows us to use spectral methods to analyze nonlinear dynamics. A bit of background, this has enjoyed great success in system identification algorithms of nonlinear dynamics, such as dynamic mode decomposition and its variance, and also in estimation, prediction, and control problems. We can use this description of generic dynamics to represent an uncertainty set as perturbations of a linear transfer operator, which is a well-studied theory in comparison to, let's say, perturbations of an arbitrary nonlinear state space map. To give an example of how this might be used, consider the standard Koopman model predictive control problem, now with a robust formulation, where we try to minimize the worst case cost over some horizon and perturbations of the linear operator k. So we basically shift the difficulty of generating this uncertainty set from arbitrary perturbations of nonlinear functions to this perturbation set delta, which are essentially additive perturbations to the transfer operator. To define this delta, we'll start by moving to a generic metric space of transfer operators. And we'll say that in general, our uncertainty set is going to be defined by a nominal Koopman operator k naught, which is along with all possible operators k, which satisfy some inclusion condition according to the metric. And this moves us to the second question, which is what is a good metric over transfer operators? And this is at the heart of our method. So in the past 20 years, there have been many metrics proposed for linear dynamical systems, and a large class of these metrics, called Binet-Cauchy kernels for the Binet-Cauchy theorem, was proposed by Vishwanathan et al. And essentially take this generic representative form, whose specific forms are often called trace or determinant kernels. In 2018, Ishikawa et al. Generalized this kernel to Perron-Frobenius operators over reproducing kernel Hilbert space. And this can be seen as a generalization of the Binet-Cauchy kernel. And this is what we will use for our method. For our purposes, we adapt this kernel to Koopman operators as follows. First, since these are uncertainty sets for essentially the same dynamics, we fix the initial conditions and we fix the observable space. And this allows us to drop the initial value and the observable operators in the RKHS from the metric. Second, since the Koopman operator is bounded, but the Perron-Frobenius operator is bounded, but the Koopman operator is not, we will need to introduce this exponential discounting term, which ensures that our kernel over Koopman operator is convergent for all arguments. We will convert this unbounded kernel to a bounded metric using standard cosine similarity, and we will then define a density function on distance as follows. We simply choose some density function with bounded support, such as the beta distribution, and now we can just define our uncertainty set in a probabilistic sense by sampling transfer operators k from this density function over, which is centered at the nominal transfer operator, subject to some constraints on the distance. So the practical question of our method is how to sample this distribution. And we do so using MCMC. So the first sort of option we could take is to use the standard random walk methods such as Metropolis Hastings or Glauber dynamics. The problem with these methods is that they have dimensionality dependent reject rates. So the sample efficiency is exponentially low in the dimension. Since we will be working with matrix approximations to infinite dimensional transfer operators, which can be very high dimensional themselves, we prefer something which has a better sample efficiency. And this is where gradient-based Markov chain Monte Carlo methods can come in, for example, Langevin dynamics. A popular method in machine learning and statistics recently is a Hamiltonian Monte Carlo method, which essentially simulates Hamiltonian dynamics with Brownian motion in a potential which is defined by the stationary distribution. And to run the system, we'll simply use a symplectic integrator such as the Leapfrog. We'll run this Hamiltonian dynamics along with the Metropolis Hastings accept conditions, and this will be the MCMC method. So we run Hamiltonian dynamics in the potential induced by our distribution over transfer operators. To review a little bit what HMC requires, the first is that the metric should be differentiable everywhere in the region of interest. This is fortunately true for the class of all Binet-Cauchy type metrics that we have studied, and practically is easily accomplishing automatic differentiation. But the second, more difficult constraint is that the potential must be continuous everywhere. However, as we said earlier, there may be natural constraints to impose in the uncertainty set. The first is simply that we saw is the distance bound, but we may have other natural constraints. For example, parameter bounds in analytic dynamical models, or we may have regime constraints. So for example, on the left, we have sort of unconstrained perturbations of a limit cycle system, which is the van der Pol oscillator. And we can see that even with the metric that we have proposed, these perturbations easily venture at long times into these sort of attractor systems, which is very distinct from the original limit cycle system. In this case, we would like to impose some rules on the spectrum of the transfer operator. In this case, we want to keep it with an epsilon of 1. So this constraints induce discontinuities in the potential. And the question is, how do we deal with these discontinuities when sampling? A naive method may be to rejection sample. So we simply, as we generate our uncertainty set, we reject samples which do not satisfy the constraints. But as we mentioned earlier, this can have exponentially low sample efficiency depending on the support of the constraints. The nice thing is that with HMC, we can actually impose constraints naturally upstream in the sampling process as boundary conditions on the Hamiltonian dynamics. This is often referred to as reflective or refractive HMC, and we adapt this method by Afshar et al. To impose inequalities on arbitrary differentiable scalar functions of the sample. The method is simple. We simply use the gradient to compute a reflection plane at whenever any constraint is violated, and we elastically change the momentum of the sample whenever this constraint is hit. This allows us to now express our final uncertainty set, which are samples from this distribution of transfer operators conducted via MCMC, with arbitrary boundary conditions imposed by these scalar constraints. A couple of notes on the practical implementation of our method. We can exploit parallelism, which can be important when the samples are high dimensional, by simply doing a pre-run of this method in a uniform prior to generate initial conditions, and then generating batches. And we can then recombine these batches using a standard Metropolis-Hastings criterion. Another nice thing is that for experimental purposes, any differentiable metric can be used. We compare our Koopman kernel with the standard trace kernel as a sort of as a comparison, but any differentiable metric is possible. And lastly, this kernel in particular can be used either with transfer operator directly or with observation sequences. And one can be more convenient to use than the other, depending on the application. And finally, we'll show some results of this method. We'll start with the toy linear time invariant 2x2 system, since it's really easy to visualize what's going on via the trace determinant plane. Both the baseline and the proposed method here will use exactly the same MCMC sampling procedure proposed, except we'll simply compare the choice of metric. On the top, we have the traced kernel, which corresponds to norm-bounded perturbations in the metric on R2x2. On the bottom, we have the proposed Koopman kernel. Both methods perform similarly, except in the structurally unstable case, where we have that the baseline method easily ventures into distinct attracting or diverging regimes, whereas the proposed method keeps the structurally unstable system centered at the axis, preserving its oscillating behavior. This suggests that it preserves the limit behavior better than the default metric. Moving to a nonlinear example with the unforced Duffy equation, on the left, we see that the default metric results in perturbations that do not preserve attractive structure in the majority of cases, and some examples are even diverging. Whereas on the right, with the proposed Koopman kernel, we have the attractive structures preserved in the majority of cases, along with some warping of the underlying potential well, which may have physically meaningful interpretations. And finally, on a limit cycle system, such as the van der Pol oscillator, we have that the default metric results in perturbations which easily venture into attracting or diverging regimes, whereas the Koopman kernel, along with a constraint on the spectral radius centered at 1, preserves the limit cycle behavior much better. So to summarize the uncertainty set generation procedure, we began by moving to a transfer operator description in an arbitrary metric space, constructing a distribution on distance using this metric around nominal, and then sampling this distribution using Hamiltonian Monte Carlo with boundary conditions. And use cases of this method may be where a parameterization or otherwise a prepared uncertainty set may not exist. And this can be used in robust control, prediction, and estimation, or pipelines involving uncertain system identification. And finally, we see this as a supplement to traditional uncertainty quantification methods, since we do not require any additional data to construct the uncertainty set. Thank you.